Every detail in this story comes from real scientific research and observation. A telegraph line hisses to life with no battery connected to it. Paper begins to smoke on a desk inside a telegraph office in Boston. An operator in Washington feels a jolt of current travel up his arm before his hand ever touches the key. In the Rocky Mountains, gold miners climb out of their bunks at 1 a.m, certain that the sun has already risen. Above Havana, a curtain of deep red light bends across a sky that has never once held the aurora before. Ships far out on the Atlantic lose their compass headings entirely, the needles spinning with no north to find. Alone at a telescope in the English countryside, an astronomer named Richard Carrington watches something on the surface of the sun that no human being has ever recorded. 2 beads of blinding white light appear where sunspots had been a moment earlier. Then, in less than 5 minutes, they are gone. A pen tied to a magnetized needle in an observatory near London jumps without any hand touching it. 17 hours later, the planet is not the place it was that morning. Somewhere above the atmosphere, a wall of charged particles is already arriving. Telegraph wires from Maine to Texas begin operating on their own, carrying messages without any battery power behind them. Sparks leap from telegraph equipment in Philadelphia, bright enough to set paper alight. An operator in Boston is knocked backward by a shock delivered through his own key. Aurora, usually confined to the far north, blazes over the Caribbean, bright enough for people to read a newspaper by its light at 1 a.m. Miners in Colorado start cooking breakfast under a false dawn that refuses to end. Sailors on ships in the mid-Atlantic watch their compass needles spin freely, pointing nowhere at all. And on the surface of a star 93 million miles away, a magnetic field has just torn itself apart and reconnected, releasing more energy in a few minutes than humanity has ever produced in its entire existence. No satellite tracked it, no power grid strained under it, because none existed yet. Only copper wire, magnetized needles, and the night sky itself bore witness. This is the story of the day the sun reached across the solar system and touched nearly everything human beings had built. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Everything in tonight's episode is grounded in documented scientific research, historical telegraph records, and the astronomical observations of the people who witnessed it. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. On September 1st, 1859, the strongest geomagnetic storm ever recorded reached the Earth. It became known as the Carrington Event, named for the English astronomer who first observed the solar flare that triggered it. The storm itself was not a local event. It unfolded across the entire planet at once, from telegraph offices along the eastern coast of the United States to fishing villages in the Caribbean, from British shipping lanes to the gold fields of the American West. It happened at the very beginning of the telegraph age, when copper wire had only just begun stitching distant cities together into something resembling a nervous system. The first commercial electric telegraph lines had gone into service only a little more than 2 decades earlier, in the late 1830s and early 1840s, and by 1859, the technology had spread with extraordinary speed. Tens of thousands of miles of telegraph wire now cross the eastern United States alone, strung on wooden poles along railway lines and roadways, carrying news, business orders, and personal messages at a speed no communication technology had ever achieved before. A message that once took days or weeks to travel by horse or ship could now cross a continent in minutes, encoded as pulses of electric current tapped out in Morse code and carried down a single strand of copper wire. Just 1 year earlier, in August of 1858, engineers had briefly succeeded in linking Europe and North America by a telegraph cable laid across the floor of the Atlantic Ocean, a feat celebrated with fireworks and church bells before the cable's insulation failed within weeks and severed the connection. The world, in other words, had just begun to wire itself together and had not yet discovered how vulnerable that wiring might be to something entirely outside human control. For the first time in recorded history, it became possible to see, in real time, how directly a star 93 million miles away could reach into human infrastructure and disrupt it. In more than a century and a half since, nothing observed has matched its scale. It began in a private observatory in the English countryside on a clear late summer morning that seemed at first like any other. Richard Carrington was 33 years old in 1859, the son of a wealthy London brewer who had studied mathematics at Cambridge with the intention of entering the clergy. He abandoned that path partway through his studies, drawn instead toward astronomy, a field that in the middle of the 19th century still relied almost entirely on patient, unpaid observers working from private estates rather than salaried professionals working in state institutions. Using part of his family's fortune, Carrington built a private observatory at Red Hill in Surrey, south of London, and equipped it with a refracting telescope fitted for a single methodical purpose: tracking the positions and movements of sunspots across the face of the sun day after day for years. His timing was fortunate in a way he could not have known. 16 years earlier, in 1843, a German pharmacist and amateur astronomer named Heinrich Schwabe had published 17 years of his own sunspot records, revealing for the first time that the number of visible sunspots rose and fell in a roughly 11-year cycle. That discovery had transformed sunspot counting from an idle curiosity into a serious scientific pursuit, and by the time Carrington began his own systematic observations in 1853, a small international community of astronomers was racing to understand what drove that cycle and what, if anything, sunspots meant for the Earth. Carrington approached the work with unusual rigor. Rather than simply counting spots, he measured their precise positions on the solar disk day after day, a project that would eventually allow him to make his own major discovery: that the sun does not rotate as a solid body, but spins faster at its equator than near its poles, a phenomenon now called differential rotation. That discovery was still 4 years away in September of 1859. On this particular morning, Carrington's task was more immediate. Sunspots are regions on the sun's visible surface, the photosphere, where intense magnetic fields suppress the flow of hot plasma rising from below. Because that suppressed plasma cannot carry heat upward as efficiently as the surrounding surface, sunspots appear darker, cooler by comparison, though still several thousand degrees Celsius themselves. By 1859, astronomers had already begun to suspect that sunspots followed some kind of cycle, rising and falling in number over roughly a decade, though the underlying magnetic mechanism driving that cycle would not be understood for decades more. Carrington's method was careful and repetitive. Each clear morning, he projected an image of the sun through his telescope onto a screen inside the observatory, tracing the outlines of visible sunspots by hand and recording their positions against a ruled grid. It was slow, exacting work, the kind that produces long tables of numbers rather than dramatic discoveries. On the morning of September 1st, Carrington was tracking an unusually large and complex group of sunspots, one that had been growing in size and tangled magnetic structure for several days. By some estimates, the group spanned an area several times larger than the Earth itself, a dark, knotted region of intense magnetic activity near the sun's equator, its structure twisted by magnetic field lines, wound tighter with each rotation of the solar surface beneath it. Astronomers of Carrington's era had no way to measure magnetic fields directly on the sun. That instrument, the spectrohelioscope, would not exist for another 60 years. What Carrington could see and record with his pencil was only the visible consequence of that hidden magnetic tension, a darker, more complex patch on an otherwise blazing surface, one that seemed, by the first days of September, to be building toward something. Each sunspot in the group showed the same basic structure astronomers still describe today, a dark central core called the umbra, where the magnetic field runs most nearly straight up out of the surface and suppresses convection most strongly, surrounded by a lighter, textured ring called the penumbra, where the field lines tilt outward at a shallower angle. A single large sunspot can be wider than the entire Earth, a complex multi-spot group of the kind Carrington was tracking that week, with several umbral cores tangled together within one penumbral boundary, represents a region where opposing magnetic polarities have been dragged close together by the roiling motion of plasma below, storing enormous energy in the twisted field between them, energy with nowhere to go but out. At around 18 minutes past 11, local time, Carrington was sketching the outline of the sunspot group when he noticed something he had never seen before in years of daily observation. 2 points of light, brilliant and white, appeared suddenly within the sunspot group itself, far brighter than the surrounding solar surface. For a moment, he assumed a flaw in his equipment, a stray reflection, a flash from outside the observatory. He checked and found nothing wrong with the telescope or the projection screen. What he was watching was happening on the sun itself. The 2 bright points intensified rapidly, moved slightly across the sunspot group, and then began to fade. Carrington later estimated that the entire event lasted around 5 minutes, from the first appearance of the light to its complete disappearance. He was not the only person to see it. Roughly 60 miles away, an amateur astronomer named Richard Hodgson was independently observing the same sunspot group at the same time and recorded a strikingly similar white light flash. Neither man had a name for what he had witnessed, because no one did yet. What Carrington and Hodgson had seen, without knowing it, was the first solar flare ever observed and documented by human beings. The fact that 2 independent observers, 60 miles apart, recorded the same brief event at the same moment mattered enormously to the scientific community that examined their accounts afterward. A single observer might have been mistaken, a trick of a lens, a flaw in glass, a momentary illusion. 2 observers, working with different instruments in different locations, describing the same phenomenon in the same 5-minute window, could not easily be dismissed. When Carrington and Hodgson each submitted their accounts to the Royal Astronomical Society, the Society published them side by side in its monthly notices that November, alongside Carrington's careful sketches of the sunspot group and the timing of the flash, recorded to the minute. At the meeting where the accounts were first read aloud, the response from other astronomers present was, by surviving records, one of interested caution rather than excitement. A single bright flash on the sun, however striking, was not yet understood to mean anything beyond itself. Solar physics as a discipline barely existed in 1859. The sun was still treated largely as a fixed, unchanging backdrop against which the planets moved, not as an active, violent body capable of reaching outward and touching the Earth directly. Carrington himself, in his written account, was notably restrained. He described what he had seen in precise, measured language, noted the coincidence with the Q magnetometer, and explicitly cautioned his colleagues against reading too much into a single correlated event, famously writing that one swallow does not make a summer, nor one observation a scientific certainty. It was a scientifically responsible thing to say. It also happened to be wrong, though Carrington would not live to see how wrong, nor would most of his contemporaries fully grasp the connection between solar flares and geomagnetic storms until well into the 20th century, when spacecraft finally allowed scientists to observe the sun's outer atmosphere directly. A solar flare is a sudden, intense burst of radiation released when the sun's magnetic field lines, twisted and stressed by the churning plasma beneath the surface, break and violently reconnect. That reconnection releases stored magnetic energy across the entire electromagnetic spectrum at once, from radio waves through visible light to X-rays and gamma rays, all within a span of minutes. The white light flash that Carrington and Hodgson recorded was simply the visible light portion of that release, and its visibility alone said something important about the scale of the event. The photosphere, the sun's visible surface, already glows at a temperature of roughly 5,500 degrees Celsius, bright enough that almost nothing occurring on it can appear brighter by comparison. For a flare's light to stand out clearly against that background, as Carrington's did, the energy released has to be extraordinary. Even now, white light flares bright enough to see without specialized filters remain rare, a small fraction of the thousands of flares recorded by modern solar observatories each year. Carrington did not know in that moment that he had witnessed only the first half of the event. A flare of that scale is very often accompanied by something far larger and slower, a coronal mass ejection, a vast cloud of magnetized plasma hurled outward from the sun's outer atmosphere into space. He recorded the sunspot positions, noted the strange flash in his log with careful scientific restraint, and went about the rest of his day, unaware that he had just watched the opening moment of the most powerful geomagnetic storm in recorded history begin its journey toward Earth. Carrington did make one further observation before the day ended, and it would later prove significant. He noted that a magnetometer at the Kew Observatory near London, an instrument used to record small fluctuations in Earth's magnetic field, registered a sudden disturbance at almost exactly the same moment as the flare. The Kew instrument worked by a method that was, for its era, remarkably elegant. A small mirror was suspended within a magnetized needle assembly, and a beam of light reflected off that mirror onto a slowly moving strip of photographic paper, tracing a continuous line that recorded the faintest shifts in Earth's magnetic field through the day and night without any human observer needing to watch it constantly. At the moment of Carrington's flare, that line jumped. A sudden sharp deviation appeared on the Q recording, lasting only a few minutes, in a pattern that decades later would come to be known among solar physicists as a magnetic crochet, a brief disturbance caused by a burst of X-ray radiation from a flare striking the Earth's upper atmosphere at the speed of light only 8 minutes after leaving the Sun. It was a strange coincidence at the time, one that Carrington mentioned cautiously in his written account, aware that a single instrument twitching at the same moment as a solar event did not, on its own, prove any connection between the two. He was right to be cautious. He was also, as it would turn out within a day, correct, though the true confirmation would not come from a twitching needle on a strip of paper, but from something far larger, moving far more slowly, already crossing the 93 million miles of space between the Sun and the Earth. Carrington closed his observation log that afternoon, much as he had on any other day, recording the sunspot positions in his careful hand, noting the strange white flash as an anomaly worth further study, and returning to the ordinary business of a Victorian gentleman scientist. He had no reason yet to connect his observation to anything happening beyond his own telescope. Sunspots, in the scientific understanding of 1859, were curiosities of the solar surface, interesting for what they revealed about the Sun itself, but not yet understood to have any direct physical connection to events on Earth. That evening, as the sun set over Surrey, England, looked much as it had the evening before: gas-lit streets, horse-drawn traffic, telegraph offices closing for the night with their equipment quiet. Carrington dined, wrote letters, and by all surviving accounts gave no outward sign that the day had been anything but a productive one for a man who spent his life patiently charting a star most people never thought to look at closely. There is something worth sitting with in that quiet, ordinary evening. A single careful observer, hunched over a notebook in a country observatory, had just recorded the opening seconds of an event that would touch nearly every telegraph wire on 2 continents, and he had no way of knowing it yet. Modern solar physicists, studying the Q magnetogram and Carrington's own sketches more than a century later, have reconstructed what was almost certainly happening on the Sun in the hours after the flare, invisible to any observer of the time. The same magnetic violence that produced the white light flash had very likely also hurled a vast cloud of magnetized solar plasma outward into space, a coronal mass ejection following close behind the flash of light and radiation that Carrington had already seen. Unlike the flare's radiation, which travels at the speed of light and reaches Earth in about 8 minutes, that cloud of plasma would travel far more slowly, carried outward by the force of its own eruption, dragging a tangled magnetic field behind it like the wake of a ship. Under ordinary circumstances, a coronal mass ejection launched from the Sun takes 2 to 4 days to cross the 93 million miles separating the Sun from the Earth, if it is aimed at the Earth at all, which most are not. What made September of 1859 extraordinary was that these were not ordinary circumstances, and the cloud now moving outward from the sunspot group Carrington had been sketching was not going to take days to arrive. By the time Carrington folded away his notebook that evening, the storm that would soon be named after him was already less than a day from Earth, moving through the dark at a speed that nothing in the solar system moves at without a reason. That reason, and the extraordinary physics that allowed a cloud of solar plasma to cross 93 million miles of space in a fraction of the usual time, is where this story continues. Roughly 17 and a half hours after Carrington watched those two beads of white light fade from the surface of the sun, the storm that Flare had launched would reach the Earth, and the ordinary world of September 1859 would end. But that arrival and the physics that made it possible is where the next part of this story begins. To understand why the cloud now crossing the solar system was moving faster than anything of its kind had moved before, it helps to understand what a solar flare and a coronal mass ejection actually are at the level of physics rather than appearance. The sun is not a solid object. It is a sphere of plasma, matter so hot that electrons have been stripped from their atoms, leaving behind a churning soup of charged particles that conducts electricity and responds strongly to magnetic fields. Beneath the visible surface, that plasma rises and falls in enormous convective cells, roughly the way water circulates in a pot brought to a rolling boil, except on a scale where a single convective cell can be wider than several Earths placed side by side. As that plasma churns, it drags the sun's magnetic field along with it, twisting and stretching field lines that would otherwise run in simple, smooth arcs from one magnetic pole to the other. Where the plasma motion is especially turbulent, as it is around a large sunspot group, the magnetic field can become knotted, almost like a rope wound, too many times around itself, storing more and more energy in its own twisted geometry with every hour that passes. Eventually, that geometry becomes unstable. When magnetic field lines of opposite polarity are pressed close enough together, they can suddenly and violently reconnect, snapping into a simpler configuration and releasing the energy that had been stored in their twisted shape, in much the same way a rubber band releases stored energy the instant it snaps. This process, called magnetic reconnection, is the central engine behind a solar flare. It converts magnetic energy into heat, light, and the kinetic energy of accelerated particles almost instantaneously on a scale that is difficult to render in ordinary terms. A large solar flare can release energy equivalent to billions of 1 megaton nuclear weapons detonating simultaneously, radiated outward across the entire electromagnetic spectrum within a span of minutes. Modern solar observatories classify flares by their X-ray brightness, using a scale that runs from the smallest, labeled A class, through B, C, and M, up to the most powerful category, X-class flares, each letter representing approximately a tenfold increase in energy over the one before it. Based on later analysis of the Q magnetometer's sudden deviation and the brightness Carrington described, solar physicists now estimate the September 1859 flare would rank among the strongest X-class events ever inferred, comparable to or exceeding the largest flares directly measured by spacecraft in the modern satellite era. The comparison is a striking one. A flare witnessed by a single man with a pencil and a projection screen in 1859 stands, in terms of raw energy, alongside the most powerful eruptions modern instruments have ever recorded from orbit. Today, coronal mass ejections are tracked directly by spacecraft such as the Solar and Heliospheric Observatory, positioned nearly 1 million miles from Earth, using an instrument called a coronagraph that blocks out the sun's overwhelming direct light with a small occulting disk, allowing the much fainter corona around it and any eruption moving through it to be photographed in real time. Carrington had no such instrument. Every detail he recorded came from watching an ordinary, unfiltered image of the sun projected onto a screen, catching by chance the few minutes in which the flare's visible light happened to be bright enough to see at all. That he documented anything at all was less a matter of specialized technology and more a matter of habit, a disciplined observer at his telescope at the right moment on a morning that could easily have been cloudy or busy with other obligations or simply overlooked. That energy travels as light and radiation at the fastest speed physics allows, reaching Earth in about 8 minutes, regardless of the size of the flare, which is why the disturbance on the Q magnetometer appeared at almost the same instant Carrington saw the white flash through his telescope. The X-ray and ultraviolet radiation from the flare had struck the Earth's upper atmosphere and briefly altered its electrical properties, producing the small, sharp deviation recorded on the magnetometer's photographic strip. But radiation is only the fastest part of what a major flare can unleash, and often the least consequential for a planet's surface, since Earth's atmosphere absorbs most high-energy radiation before it can reach the ground. The larger threat, and the one that would determine what happened over the following 17 hours, moves far more slowly and far more massively. A coronal mass ejection is exactly what its name describes, a mass of the sun's outer atmosphere, the corona, ejected outward into space, carrying with it billions of tons of magnetized plasma. Where a flare releases energy as light, a coronal mass ejection releases matter itself, hurling an enormous cloud of charged particles and tangled magnetic field outward from the sun at speeds that can range from a few hundred to more than 2,000 kilometers per second, depending on the violence of the eruption that launched it. The total mass involved is difficult to picture in ordinary terms. A large coronal mass ejection can carry outward somewhere between 1 and 10 billion tons of solar material, plasma torn free of the sun's outer atmosphere and flung into interplanetary space as a single, semi-coherent cloud still bound together by its own embedded magnetic field, even as it expands across millions of kilometers. To put that mass in perspective, it is comparable to roughly the combined weight of every ship in every navy on Earth, repeated many thousands of times over, accelerated to a speed of thousands of kilometers per second, and sent outward in a single direction. And yet, spread across the enormous volume the cloud occupies by the time it reaches Earth's orbit, that same plasma is, paradoxically, thinner than the air inside a laboratory vacuum chamber, a reminder that even an event of planetary consequence can be, at the level of individual particles, almost unimaginably sparse. Modern solar physicists studying the Carrington Event, using the historical magnetometer records and the timing of Carrington's own observation, have estimated that the coronal mass ejection following the September 1st flare was moving at somewhere close to 2,500 kilometers per second, among the fastest ever inferred for any solar eruption, before or since. At that velocity, the cloud would cover the 93 million miles between the Sun and the Earth in a fraction of the time such a journey normally requires. Under typical conditions, a coronal mass ejection aimed at Earth takes somewhere between 2 and 4 days to arrive, its plasma cloud slowed gradually by friction with the thin, ever-present stream of particles flowing outward from the sun in every direction, known as the solar wind. The ordinary solar wind is remarkably tenuous by earthly standards, typically carrying only a handful of particles, often fewer than 10, in every cubic centimeter of space near Earth's orbit, moving at an average speed of around 400 kilometers per second. Thin as it is, that constant outward pressure is enough to shape comet tails, compress planetary magnetic fields, and fill the space between the planets with a faint, steady headwind that any fast-moving cloud of ejected solar material must push through. A coronal mass ejection moving at ordinary speed loses much of its momentum to that headwind over the course of its journey, arriving at Earth slowed and diffused compared to the moment it left the Sun. The 1859 ejection covered that same distance in approximately 17.5 hours, arriving at the Earth on the morning of September 2nd, less than a full day after Carrington had watched its originating flash fade from his telescope. Solar physicists studying the event more than a century later found a likely explanation for that extraordinary speed, one that had nothing to do with the September 1st flare itself. 4 days earlier, on August 28th, the same active region of the Sun had produced an earlier, somewhat smaller coronal mass ejection, one that received far less attention at the time because it produced no dramatic white light flash for anyone to observe directly. That earlier ejection, astronomers now believe, swept much of the slower solar wind plasma out of the path between the Sun and the Earth, clearing a kind of channel through the interplanetary medium. When the second, much larger ejection launched on September 1st, it encountered far less resistance along that same path, allowing it to maintain a far higher speed across the entire 93 million mile crossing than it otherwise could have. It is a piece of cosmic timing that solar physicists still consider remarkable. Not one eruption, but two, launched days apart from the same region of the Sun, the first unknowingly clearing the road for the second. Had the August 28th ejection not occurred, or had it been aimed in a different direction, the September 1st storm might have taken 2 or 3 times as long to arrive, and very likely would have been considerably weaker by the time it reached Earth's magnetic field. Instead, a cloud of plasma with a mass on the order of Mount Everest, repeated many billions of times over, carrying its own embedded magnetic field, was now closing the final distance to Earth at a speed of nearly 9 million kilometers per hour, and the planet it was approaching had almost no capacity to see it coming. There were no satellites in 1859 to detect an incoming coronal mass ejection, no instruments positioned between the Sun and the Earth to provide even a few hours of warning. The only planetary scale structure standing between that oncoming cloud and the surface of the Earth was one that no human being could see directly, and few at the time understood existed at all: the Earth's magnetosphere, a vast, invisible bubble of magnetic influence generated deep within the planet itself. Earth's magnetic field originates close to 2,900 kilometers beneath the surface, in the outer core, a layer of molten iron and nickel that flows and churns as the planet rotates. That churning motion generates electric currents, and those currents in turn generate a magnetic field through a self-sustaining process known as the geodynamo, the same basic mechanism on an immensely larger scale that produces a magnetic field around any electromagnet built from coiled, current-carrying wire. The outer core itself is under conditions almost impossible to picture from the surface, temperatures reaching somewhere near 4,000 degrees Celsius, similar to the surface of the Sun itself, and pressures more than 1,000,000 times greater than at sea level, all acting on a layer of liquid metal about 2,000 kilometers thick. At those temperatures, iron and nickel exist above what physicists call the Curie point, the temperature beyond which a material loses any fixed, permanent magnetism of its own. The Earth's magnetic field is therefore not a simple static magnet buried underground, as early scientists sometimes imagined, but an active, continuously regenerated field sustained only by the ongoing motion of molten metal driven by the planet's rotation and its slowly escaping internal heat. Stop that motion even briefly, and the field would begin to decay within a matter of centuries, a fact that underscores just how dynamic and fragile a process quietly protects the surface of the Earth at every moment, including the moment in the early hours of September 2nd, 1859, when it was about to be tested more severely than at any other point in recorded history. The field produced by that process extends far beyond the planet's solid surface, reaching tens of thousands of kilometers into space, and forming a protective structure that shields the Earth's atmosphere from the constant stream of charged particles flowing outward from the sun. Under ordinary conditions, the solar wind flows past this magnetic bubble the way a stream flows around a rock, deflected around the Earth rather than striking it directly, compressing the magnetosphere slightly on the side facing the sun and stretching it into a long tail on the side facing away, a shape that has been mapped in detail by spacecraft over the past several decades. On the side facing the sun, the solar wind first encounters a standing shock front called the bow shock, a boundary where the supersonic flow of particles abruptly slows and turns, not unlike the shock wave that forms ahead of a boat moving faster than the waves it creates in open water. Just inside that shock lies the magnetopause, the true outer boundary of the magnetosphere itself, typically located around 60,000 kilometers from Earth on the sunward side under calm conditions, a distance equal to about 5 Earth diameters. Behind the planet, on the side facing away from the sun, the magnetic field stretches out into a long magnetotail that can extend for millions of kilometers, reaching well beyond the orbit of the moon, shaped by the constant pressure of the solar wind flowing past. None of this structure was known or even suspected in 1859. The idea of a magnetosphere would not be formally proposed until the 20th century, and the radiation belts trapped within it, regions where the Earth's field captures and holds charged particles in orbit around the planet, would not be discovered until 1958, when the first American satellite, Explorer 1, carried a radiation detector into orbit and found readings so far beyond expectation that its designer, James Van Allen, initially suspected his instrument had failed. In Carrington's era, the Earth's magnetic field was understood only through its faint, indirect effects, the gentle deflection of a compass needle, the occasional appearance of aurora at high latitudes, and the slow, steady traces left on instruments like the one recording at Kew. No one in September of 1859 had any concept of a magnetopause or a magnetotail, let alone the idea that a cloud of solar plasma might tear a temporary hole through that invisible structure. That everyday interaction is gentle enough that it produces only the faint, familiar aurora seen occasionally near the Earth's poles, where the magnetic field naturally funnels a small number of charged particles down into the upper atmosphere. A coronal mass ejection moving at nearly 9 million kilometers per hour, carrying its own powerful embedded magnetic field, is not a gentle interaction. When such a cloud strikes the magnetosphere, particularly if the magnetic field embedded within the cloud is oriented opposite to Earth's own field, the two fields can connect and merge in a large-scale version of the same reconnection process that triggered the original flare on the sun, tearing open a temporary breach in the planet's magnetic shield and allowing enormous quantities of solar particles and energy to pour into the space around Earth. Modern heliophysicists describe this orientation using a measurement called the interplanetary magnetic field's north-south component, often written simply as BZ. When the magnetic field embedded in an arriving solar wind or coronal mass ejection points northward, in roughly the same direction as Earth's own field near the equator, the two fields resist merging, and much of the incoming energy is deflected harmlessly around the planet, similar to how two magnets pushed together, North Pole to North Pole, resist joining. When that embedded field instead points southward, opposite to Earth's own field, the two can connect efficiently, and the strength of the resulting geomagnetic disturbance depends heavily on how strongly southward that field is, and for how long the orientation persists as the cloud sweeps past. Scientists reconstructing the Carrington Event from historical magnetometer data believe the 1859 cloud arrived with an unusually strong and prolonged southward field, one of several factors, along with its extreme speed and mass that combined to make the resulting storm the most powerful ever recorded, rather than merely a strong one. It was, in effect, a worst-case alignment of several independent variables: exceptional speed, enormous mass, and a magnetic orientation almost perfectly suited to breaching Earth's defenses, arriving together in a single event. Much of what is now understood about the true scale of the 1859 storm did not come from Carrington's telescope or the Q magnetometer alone, but from evidence left behind in places no observer of the time thought to look. Deep within the ice sheets of Greenland and Antarctica, layers of snow compress over centuries into solid ice, trapping tiny quantities of whatever chemicals were present in the atmosphere at the moment each layer fell. Energetic particles striking the upper atmosphere during a major geomagnetic storm produce measurable spikes in certain chemical markers, including nitrate compounds and a rare isotope called beryllium-10, both of which settle out of the atmosphere and become locked into the ice within months. By drilling ice cores and counting backward through the annual layers to the year 1859, modern researchers have located a distinct spike in these markers precisely where the Carrington Event should appear, an independent confirmation, preserved in ancient ice, of a storm first recorded by a Victorian astronomer's pencil and a jumping needle on a strip of photographic paper. By the early hours of September 2nd, 1859, the breach in Earth's magnetic shield was forming, though no person on the ground yet knew it. Carrington, back at his own observatory, had resumed his usual routine of morning sunspot sketches, unaware that the cloud his flare had launched the previous day was now only hours from arrival. Telegraph operators across 2 continents were settling into an ordinary overnight shift, checking their equipment, sending routine messages, expecting nothing unusual. In the polar regions, where Earth's magnetic field lines dip down toward the surface and normally funnel a trickle of solar particles into the atmosphere, the aurora that night was already unusually active, a pale warning glow visible to anyone who happened to look up, though almost no one watching it yet understood what it meant. Within the hour, that glow would begin spreading toward latitudes where no one alive had ever seen it before. The cloud itself, by the time it reached Earth's orbit, had expanded enormously from the compact eruption Carrington witnessed the previous morning, its magnetized plasma now spread across a front many millions of kilometers wide, far larger than the planet it was about to strike, so that Earth would not so much be grazed by the storm as fully engulfed within it. None of the people about to experience that engulfment could have known it was coming. There were no warnings possible in 1859, no way to measure a storm racing toward them from 93 million miles away. What happened next unfolded simultaneously across an entire hemisphere, in telegraph offices and mountain camps and ships at sea, all reached at nearly the same moment by a force none of them could see, only feel in the sudden, inexplicable behavior of their own instruments and their own night sky. In telegraph offices across the northeastern United States, the first sign that something was wrong was not a message, but a shock. Operators reported feeling electric current arc from their equipment, even when no battery was connected, sparks jumping from the metal contacts of their keys, and in several documented cases, small fires breaking out where sparks ignited paper tape or dry wood casing. One of the best documented exchanges of that night took place on the line connecting Boston and Portland, Maine, operated by the American Telegraph Company. An operator in Boston, noticing that the line seemed to be carrying a strange current of its own, proposed an experiment to his counterpart in Portland: disconnect the batteries that normally powered their signals and see whether the line would still carry messages using only whatever current the storm itself was inducing in the wire. It worked. For a period later reported as lasting well over an hour, the two operators exchanged messages using no battery power at all, the geomagnetic storm itself acting as the power source for their entire telegraph line. The two men are said to have found the situation more curious than alarming, treating the disconnection as a kind of experiment in itself, unaware that they were witnessing, in real time, a direct demonstration of a physical principle that would not be fully explained for decades: a changing magnetic field, sweeping across a long conductor, induces an electric current within that conductor, exactly as a spinning generator induces current in a coil of wire. That principle, now called electromagnetic induction, had in fact already been described mathematically by Michael Faraday roughly a quarter century earlier, in 1831, though almost no one in a telegraph office in 1859 would have connected Faraday's laboratory experiments with coils and magnets to the storm unfolding around them. A telegraph line, especially a long one strung for hundreds of miles between cities, functions almost perfectly as the kind of conductor Faraday's principle describes. The strength of an induced current in any conductor depends on two things: how large an area the conductor's circuit encloses, and how quickly the magnetic field passing through that area is changing. A long telegraph line, running for hundreds of miles between distant cities and completed by a return path through the ground itself, encloses an enormous effective area compared to a short circuit confined to a single room, which is precisely why telegraph systems, spread across such vast distances, proved so much more vulnerable to the storm than almost any other technology of the era. The Boston to Portland line, involved in the famous battery disconnection experiment, ran for roughly 140 miles, a length that under the rapidly shifting magnetic conditions of September 1st and 2nd was more than sufficient to generate a usable, if erratic, induced current along its entire path. As the geomagnetic storm's disturbance swept across the eastern United States, the Earth's magnetic field beneath and around each telegraph line was changing rapidly, its strength and direction shifting within minutes, rather than the usual slow drift of hours or days. That rapid change induced a voltage directly along the length of every wire it crossed, a phenomenon now known as a geomagnetically induced current, or GIC, the same basic effect that, more than a century later, would become a serious concern for the operators of modern high-voltage power grids. In 1859, the induced currents were sometimes strong enough to power a telegraph line on their own, and at other times far too strong, overwhelming equipment designed to handle only the gentle current of a battery, burning out delicate components and, in the most severe cases, setting paper alight. At a telegraph office in Pittsburgh, an operator later described watching a spark leap several inches from his equipment to a nearby metal surface, followed almost immediately by a thin curl of smoke rising from a stack of paper tape resting near the instrument. He and a colleague managed to extinguish the smoldering paper before it became a serious fire, but the incident was serious enough that it was reported afterward to the telegraph company's regional office as equipment damage requiring repair before the line could return to normal service. Similar small fires, most extinguished quickly and without serious damage, were reported at telegraph offices in at least 2 other American cities that night, a detail that made its way into several newspaper accounts published in the days that followed, often framed with a mixture of astonishment and unease at the idea that the sky itself could set paper alight from a distance. At one office, a telegraph clerk later described unplugging his equipment entirely and simply watching the instrument's needle continue to twitch and swing on its own for several minutes after every wire had been physically disconnected from the line, an observation he included in his incident report, less as a complaint than as a genuine scientific curiosity, evidence, though he had no way of framing it this way himself, that the current driving the disturbance originated not from any fault in the equipment, but from the wire itself, and ultimately from the sky above it. Reports from telegraph offices in Washington, Philadelphia, and Pittsburgh described operators unable to send or receive coherent messages for hours at a time, their equipment either dead or wildly overactive, needles swinging with no message being sent at all. A telegraph superintendent in Washington later wrote that the disturbance was, in his words, of a character entirely without precedent since the telegraph had come into use, unlike anything the still young industry had encountered in its first 2 decades of operation. Some operators, particularly those who had worked the lines for several years, tried at first to diagnose the trouble using familiar methods, checking connections, testing batteries, and inspecting insulation for damage, only to find every ordinary explanation ruled out one by one as the disturbance continued unabated, regardless of what they adjusted. The disruption was not confined to North America. Telegraph lines across Europe reported similar effects that same night, including lines in France, Germany, and Norway, where operators described currents strong enough to interfere with normal operation, even with batteries fully connected and functioning. In one incident recorded in a French telegraph journal published later that year, an operator described his instrument's needle deflecting so violently that it struck the mechanical stops at either end of its swing repeatedly, producing a rapid clicking that made it impossible to distinguish any intended signal from the noise the storm itself was generating. At the Kew Observatory, the man responsible for interpreting the instrument that had first caught Carrington's attention was a physicist named Balfour Stewart, superintendent of the observatory, and one of the few scientists of the era already interested in the relationship between solar activity and terrestrial magnetism. Stewart had been recording the Kew magnetometer's output through the full duration of the storm, and in the months that followed, he became one of the first scientists to argue formally, in print, that the sudden disturbance recorded at Kew on September 1st was directly connected to Carrington's solar flare, rather than a coincidence. His analysis, cautious as it was, represented an early step toward what would eventually become the modern science of space weather, the study of how conditions on the sun directly shape conditions in near-Earth space. While telegraph offices struggled below, the sky above much of the world had become something few people alive had ever witnessed. Aurora, the glow produced when charged particles, funneled along Earth's magnetic field lines, collide with gas molecules high in the atmosphere, is ordinarily confined to a narrow band of high latitudes, visible regularly only in places like northern Scandinavia, Alaska, and northern Canada. On the night of September 1st into September 2nd, that band expanded to a degree with no equal in the historical record, before or since. Even in England, where aurora was a more familiar sight than in most of the world, observers that night described a display far beyond anything typically seen at London's latitude. A deep red glow spreading across a wide arc of sky, bright enough that several London newspapers ran detailed descriptions the following morning, some noting with a touch of local pride that the display had been visible even through the city's usual haze of coal smoke. Aurora was reported across nearly the entire United States, visible as far south as the Caribbean, with accounts from Cuba describing a sky glowing deep red for much of the night. Sailors aboard ships in the mid-Atlantic and Pacific recorded similar displays in their logs, describing curtains of red and green light, visible even at latitudes close to the equator, far from where sailors of that era expected to see anything of the kind. In the Kingdom of Hawaii, contemporary newspaper accounts described a reddish glow low on the horizon that puzzled observers who had no prior experience of aurora at all. Accounts from Jamaica and from ports along the coast of Colombia described a similar reddish light, faint but distinct, low along the northern horizon, in a part of the world where the aurora had essentially no place in local memory or folklore at all, unlike in Scandinavia or Canada, where it had long been woven into local tradition and explanation. Aboard a ship recorded in the log as sailing well south of the usual shipping lanes near the equator, the captain noted an unusual reddish haze that he initially mistook for a distant fire on the horizon, only realizing over the course of the night that the light extended across too much of the sky to be anything terrestrial. Passengers aboard the same vessel, according to a later published account, were roused from their cabins by crew members eager to share the sight, gathering on deck in the middle of the night to watch a phenomenon that, for most of them, had no place in anything they had previously read or heard about the natural world. In the Rocky Mountains of Colorado, gold miners camped near the mining town of Central City were reportedly woken by the intensity of the light just after midnight, mistaking the auroral glow for the first light of dawn. According to accounts published afterward, some of the miners began preparing breakfast and readying their tools for the day's work, only to look up and find the sky darkening again as the display faded, followed sometime later by an actual ordinary sunrise several hours after the false one. It is worth pausing on how strange that moment must have felt. Men accustomed to reading the sky by long habit, suddenly finding it lying to them. The color and intensity of aurora depend on which gas molecules in the upper atmosphere are struck by incoming particles and at what altitude the collision occurs, details that would not be fully worked out by physicists for decades after 1859. What observers that night could see, without understanding the mechanism behind it, was a sky behaving in ways that seemed to violate the ordinary order of things, darkness turning to a false, colored daylight, then back to darkness, then to true dawn, all within a single night. Newspapers across the affected regions ran extensive accounts in the days that followed, many treating the display as a wonder rather than a warning, describing crowds who had gathered in the streets of cities as far south as New Orleans to watch a sky none of them had ever seen behave this way before. In New York, one newspaper described people gathering on rooftops and in public squares well past midnight, drawn outside by neighbors who had noticed the unusual light and gone door to door to spread the word, an informal, human version of the very network of rapid communication that the telegraph lines below them were struggling to maintain. Accounts from smaller towns across the American Midwest describe similar scenes: church bells rung to wake residents, families standing in open fields watching colored light ripple slowly overhead for hours, some later writing that the display was bright enough to cast faint shadows on the ground, comparable to moonlight on a clear night. Some accounts describe a more uneasy reaction. In several American cities, newspapers reported that a portion of the public feared the display signaled some kind of religious or apocalyptic event, a reaction not entirely surprising in an era when the physical connection between the sun and the Earth's magnetic field was understood by almost no one outside a small circle of scientists, and not fully by them either. A minister in one New England town reportedly delivered an unscheduled sermon the following Sunday, addressing the display directly, reassuring his congregation that the lights, however strange, belonged to the natural order established by scientific law, rather than to any supernatural warning, a sign of how quickly even religious authorities of the time felt compelled to respond to public unease over an event no one could yet fully explain. Telegraph operators, meanwhile, had little time for wonder. Through the early hours of September 2nd, offices along the eastern seaboard continued to report equipment failures, garbled messages, and in isolated cases, damage severe enough to require replacing burned components before service could resume. By some estimates gathered from surviving telegraph company records, portions of the North American telegraph network were disrupted for several hours at the height of the storm, an outage that, in an era increasingly dependent on rapid long-distance communication for business, shipping, and news, was itself a striking demonstration of how thoroughly a single geomagnetic storm could reach into daily human affairs. With the telegraph network unreliable for stretches of that night and the following day, news of the disruption itself spread more slowly and unevenly than news typically did by 1859, often carried onward by the same ordinary means the telegraph had begun to make obsolete: newspapers delivered by rail, letters carried by ship, and word passed directly between travelers arriving in one city from another. Some East Coast newspapers did not publish full accounts of the previous night's telegraph failures until their equipment and lines had been repaired enough to receive updated reports from other cities, producing the mildly ironic situation of a communication network built to carry news instantly being, for a matter of hours, unable to report on the very event disrupting it. Merchants and shipping agents who depended on the telegraph to confirm cargo arrivals, coordinate payments, and relay urgent business instructions between cities found themselves, for a portion of that day, thrown back on slower, older methods of communication, a temporary but tangible reminder of how quickly an entire commercial system had come to rely on a technology barely 20 years old. Ships at sea faced their own quieter difficulty. compass needles, which navigators depended on absolutely for determining direction, far from any landmark, behaved erratically throughout the storm, swinging and drifting in ways that made accurate navigation temporarily unreliable. For a ship's captain relying on dead reckoning, a compass that could not be trusted for even a few hours represented a genuine hazard, one compounded by the fact that no one aboard had any way of knowing when or whether the instrument would return to normal. A ship's log from a vessel crossing the North Atlantic that week recorded the compass needle drifting by several degrees over the course of a single hour, with no apparent cause, forcing the crew to rely more heavily on celestial navigation, sightings of the stars and sun taken with a sextant until the needle settled back to something resembling its normal behavior the following day. Such disturbances were not unique to 1859. Smaller geomagnetic storms had occasionally caused similar, milder compass deviations before, and sailors of the era were generally aware that magnetic storms could affect their instruments to some small degree. What made this storm different was the scale and duration of the effect, deviations severe enough, in some reported cases, to shift a ship's estimated position by a meaningful distance over the course of a long ocean crossing, a risk that, combined with the failure of shore-based telegraph communication, left much of the Atlantic's shipping traffic that week navigating and communicating with noticeably less certainty than usual. By the following night, the most intense phase of the storm had largely passed, though weaker auroral displays and minor telegraph disturbances continued for several more days as the tail of the coronal mass ejections magnetic field swept past Earth. Geomagnetic storms of this kind rarely end in a single clean burst. As the cloud of solar plasma continues past Earth, its trailing edge still carries a diminishing but real magnetic disturbance, capable of producing smaller secondary waves of auroral activity and instrument disruption even after the initial, most violent impact has passed. Observers in several American cities reported a second, noticeably fainter auroral display on the night of September 3rd, along with brief minor telegraph irregularities, a kind of long, slowly fading echo of the storm's first and most dramatic night. What remained, once the sky and the wires had settled, was a body of first-hand testimony unlike anything solar science had ever gathered before. Astronomers' sketches, magnetometer traces, telegraph company incident reports, ship's logs, and newspaper accounts from 3 continents, all describing, from wildly different vantage points, the same 17.5-hour chain of cause and effect that had begun with 2 beads of white light on the surface of the sun. That scattered testimony might easily have remained just that, scattered, disconnected, and eventually forgotten, a strange night remembered locally and then gradually lost to time as countless smaller storms before it had been. That it did not become simply another forgotten curiosity of the 19th century owes a great deal to a quieter, less dramatic development already underway in the decades before Carrington ever looked through his telescope, a deliberate international effort to measure the Earth's magnetism systematically, continuously, and simultaneously from observatories scattered across the globe. It is that effort and the surprising figure behind it that explains why a storm from 1859 could be reconstructed in such extraordinary detail more than a century and a half later, using instruments, records, and even ancient ice that no one present that night could have imagined would ever be examined at all. The story of that effort begins not with Carrington, but with a Prussian naturalist named Alexander von Humboldt, who decades earlier had become convinced that the Earth's magnetism could not be properly understood through scattered, isolated observations made by individual astronomers working alone. In the 1830s, Humboldt began urging governments and scientific societies across Europe to establish a coordinated network of magnetic observatories, each equipped with standardized instruments recording the Earth's magnetic field continuously and simultaneously, so that a disturbance detected in one location could be compared directly against readings taken at the same moment thousands of miles away. The effort became known, somewhat dramatically, as the Magnetic Crusade, and it succeeded in establishing observatories across the British Empire, continental Europe, and beyond, each one contributing continuous, methodical data to a shared scientific project on a scale unlike anything astronomy or physics had previously attempted. Humboldt found an essential scientific partner in Carl Friedrich Gauss, the German mathematician and physicist, who developed both the mathematical theory needed to describe Earth's magnetic field precisely and a more sensitive instrument, the magnetometer, capable of detecting far smaller fluctuations than earlier compass-based devices had allowed. Gauss and his colleague Wilhelm Weber went further still, founding an organization called the Göttingen Magnetic Union in 1836, which coordinated observatories across Germany and beyond to take simultaneous magnetic readings at fixed times, several times each day, an early and remarkably ambitious example of international scientific cooperation, conducted decades before instantaneous long-distance communication of any kind existed to help coordinate it. By the time the British government funded the construction of the Kew Observatory's dedicated magnetic and meteorological facilities in the 1850s, this culture of standardized, continuous, internationally comparable measurement was already well established, a scientific infrastructure built for exactly the kind of moment that arrived on September 1st, 1859, though none of its founders could have known that in advance. That infrastructure did not emerge instantly or easily, coordinating simultaneous magnetic readings across dozens of observatories scattered from Canada to India to Australia required standardized instruments, agreed-upon measurement times, and reliable postal and shipping routes to eventually bring all of that scattered data back together for comparison, a genuinely difficult logistical undertaking in an era before instantaneous long-distance communication existed at any meaningful scale. The Kew Observatory, the very institution whose magnetometer had jumped at the same instant Carrington saw his flare, existed specifically because of this earlier international effort, staffed and equipped for the express purpose of recording exactly the kind of magnetic disturbance that swept across the planet on September 1st and 2nd, 1859. Without the Magnetic Crusade, there would have been no continuously recording instrument at Kew that morning, no photographic strip capturing the exact moment of disturbance, and very likely no way for Balfour Stewart, or anyone else, to connect Carrington's flare to the storm that followed with any scientific confidence at all. That storm, in other words, arrived at almost precisely the moment human civilization had, for the first time, built the instruments necessary to properly witness it, a coincidence of timing that historians of science still regard as remarkable. That same global network also makes it possible to say, with some scientific confidence, just how the Carrington storm compares to the geomagnetic storms of the modern era, an era with satellites, power grids, and instruments Humboldt could never have imagined. Scientists today measure the overall strength of a geomagnetic storm using a value called the Disturbance Storm Time Index, or DST, calculated from magnetometer readings at several stations positioned near Earth's equator, expressed in a unit called nanotesla, a measure of how strongly the storm has depressed the normally steady strength of Earth's magnetic field. The index is calculated using readings from 4 magnetic observatories spaced around the globe near the equator, chosen specifically for their distance from the polar regions, where local auroral currents can distort a magnetometer's reading in ways that do not reflect the storm's overall global strength. By averaging the disturbance recorded simultaneously at all 4 stations, scientists can filter out much of that local noise and arrive at a single number that reasonably represents how strongly the entire planet's magnetic field has been compressed by an incoming storm, a method built directly on the same principle of coordinated simultaneous measurement that Humboldt and Gauss had championed more than a century earlier. A quiet, undisturbed day typically shows a DST value close to 0. A moderate geomagnetic storm might push that value down to -50 or -100 nanotesla. The most severe storms of the modern satellite era, storms strong enough to cause real, measurable damage to power grids and satellites, have reached DST values in the range of -400 to -600 nanotesla, among the strongest ever directly measured by instruments built for the purpose. The March 1989 storm that knocked out the Hydro-Quebec power grid in Canada, leaving roughly 6 million people without electricity for around 9 hours, reached a DST value of approximately -580 nanotesla. The powerful storms of late October and early November 2003, sometimes called the Halloween storms, which damaged satellites and disrupted airline communications, reached a DST value of roughly -400 nanotesla. Because no DST-capable instrument network existed in 1859, scientists cannot state the Carrington Event's exact value with certainty, but reconstructions based on the surviving Q magnetometer data and other period observations place it somewhere in the range of -1600 to -1800 nanotesla, roughly 3 times stronger than the Quebec blackout storm, and the strongest value ever estimated for any geomagnetic storm in the historical or instrumental record. For comparison, a storm reaching a DST value of only -100 nanotesla, far weaker than any of the events described so far, is already enough to produce visible aurora across much of the northern United States and southern Canada, and to require modern satellite operators and power grid engineers to monitor conditions more closely than usual. The gap between that routine moderate disturbance and the reconstructed strength of the Carrington Event illustrates just how far outside ordinary experience the 1859 storm truly was, not simply a larger version of a familiar event, but an event an entire order of magnitude beyond anything modern infrastructure has yet been tested against directly. There is something worth noting in that comparison. The strongest storm modern infrastructure has actually experienced still falls significantly short of what the Earth endured in 1859, using instruments built only to detect fluctuations in a compass needle. That comparison is possible today only because of tools that go well beyond anything even Humboldt's international network could have imagined. Deep within the ice sheets of Greenland and Antarctica, as mentioned earlier, layers of compressed snow trap tiny quantities of atmospheric chemistry, including nitrate compounds and the rare isotope beryllium-10, both produced when energetic particles strike the upper atmosphere during a major solar storm. By drilling ice cores and counting backward through the annual layers to locate the year 1859, researchers have confirmed a chemical signature consistent with an extraordinarily powerful event, corroborating from an entirely independent source of evidence more than a century and a half old the picture first sketched by a Victorian astronomer and a jumping magnetometer needle. The dating itself relies on the same basic principle used to read tree rings. Each year, a new layer of snow falls and compresses beneath the weight of the layers above it, and because snowfall and atmospheric conditions shift slightly with the seasons, each annual layer carries subtle chemical and physical markers that allow researchers to count backward year by year with considerable precision, even thousands of years into the past. By identifying the layer corresponding to 1859 in ice cores drawn from both Greenland and Antarctica, thousands of kilometers apart, and finding an elevated beryllium-10 and nitrate signature in both locations simultaneously, researchers were able to confirm that the disturbance affected the entire planet's atmosphere at once, rather than being some more limited regional phenomenon, matching precisely what the sudden, worldwide reach of the storm's telegraph disruptions and aurora sightings had already suggested through purely historical evidence. The aurora itself, the most visible symptom of the entire event, owes its color and structure to a specific set of atomic processes that scientists would not fully explain until decades after Carrington's flare. When charged particles funneled down along Earth's magnetic field lines collide with gas molecules in the upper atmosphere, they transfer energy to electrons within those molecules, briefly boosting them into a higher, unstable state. As each electron falls back down to its normal, lower energy state, it releases that excess energy as a photon of light, with the specific color determined by which gas molecule was struck and at what altitude the collision occurred. Oxygen atoms, when excited at altitudes of around 100 to 300 kilometers, tend to emit a distinctive green light, the color most commonly associated with ordinary aurora and the one most familiar from modern photographs taken in Alaska, Norway, and Canada. At higher altitudes, above roughly 200 kilometers, oxygen instead tends to emit a deeper red light, a less common and generally fainter glow that requires either especially energetic particles or an especially thin, high-altitude atmosphere to produce invisible quantity. Nitrogen molecules, when struck under sufficiently energetic conditions, can produce blue and deep violet light, most often visible along the lower, rippling edges of a bright auroral display, rather than across its broad upper curtain. The altitude at which each color appears follows directly from the density of the atmosphere at that height. Near the top of the auroral display, where the atmosphere is extremely thin, excited oxygen atoms have more time before colliding with another particle, allowing the slower, red light-producing transition to complete before that energy is lost some other way. Lower down, where the atmosphere is denser and collisions between particles happen far more frequently, that slower red transition rarely has time to occur, and the faster green transition dominates instead, which is why a typical strong aurora displays green along its lower and middle structure and red only along its highest, faintest reaches. The specific gases and altitudes involved also explain why aurora is essentially never seen in colors like blue-green or orange in significant quantity. The visible spectrum of an aurora is not an artistic palette, but a direct physical fingerprint of which atmospheric gas absorbed the incoming energy and at what height it did so. The overwhelmingly red character of the aurora, reported during the Carrington Event, described in accounts from Cuba, Hawaii, Colombia, and the southern United States, is itself scientifically informative, consistent with an unusually intense influx of energetic particles penetrating deep into the upper atmosphere and exciting oxygen at the higher altitudes associated with red emission rather than the more common green. It is also consistent with the aurora being pushed to such unusually low latitudes in the first place, since a storm powerful enough to compress Earth's magnetic field dramatically can extend the auroral oval, the normally narrow, ring-shaped zone of auroral activity around each magnetic pole dramatically outward toward the equator, allowing red, high-altitude emission ordinarily confined to polar regions to become visible from places like Havana or Bombay. Under quiet conditions, the auroral oval sits centered on Earth's magnetic pole, which is offset somewhat from the geographic pole, typically spanning a band of latitude that includes northern Scandinavia, Iceland, Alaska, and northern Canada, while remaining entirely invisible from the middle latitudes where most of the world's population lives. As a geomagnetic storm strengthens, more of the magnetosphere's stored energy is dumped into the upper atmosphere, and the oval expands outward like ripples spreading from a stone dropped in water, its edge creeping toward the equator in direct proportion to the storm's intensity. During the most severe recorded storms of the modern era, the oval has expanded far enough to bring faint aurora to observers in the southern United States or southern Europe, a genuine rarity that draws considerable public attention whenever it occurs. During the Carrington Event, the expansion was so extreme that the oval's edge reached almost to the equator itself, a distortion of Earth's magnetic environment so severe that, according to later reconstructions, it may have briefly compressed the sunward edge of the magnetosphere to within a few Earth radii of the planet's surface, far closer than the orbit of many satellites operate at today, though of course none existed yet to be endangered by it. Carrington himself never fully knew how this story would end, in the sense that the deeper science explaining what he had witnessed was still decades away from being understood in his own lifetime. The event he witnessed did not even carry his name during his own lifetime, or for a long while afterward. For decades, the storm was referred to simply as the Great Magnetic Storm of 1859, one of several notable disturbances mentioned in passing in scientific literature on geomagnetism, without any special distinction setting it apart as the largest such event ever recorded. It was only in the second half of the 20th century, as solar physicists gained the tools to properly measure and compare geomagnetic storms across history, that the true extremity of the 1859 event became clear, and researchers began referring to it consistently as the Carrington Event, in recognition of the astronomer whose careful documented observation had provided the crucial link between a specific solar flare and the storm that followed it. That renewed attention transformed the event from a historical curiosity into something closer to a benchmark, the reference point solar physicists and engineers now use whenever they need to describe the practical upper limit of what a geomagnetic storm might do, a role Carrington could not possibly have anticipated when he sat down at his telescope that September morning simply to continue a project of patient daily measurement. Modern researchers examining historical records have also identified evidence of storms in earlier centuries that may have rivaled or even exceeded the intensity of the 1859 event, preserved not in telegraph logs, which did not yet exist, but in the same kind of ice core chemical signatures used to confirm the Carrington Event itself, along with historical accounts of unusually widespread aurora recorded in medieval and ancient chronicles from China, the Middle East, and Europe. What makes 1859 uniquely valuable to modern science is not necessarily that it was the single largest such storm in all of human history, but that it was the first one to occur after humanity had built both the instruments capable of measuring it precisely and the technological infrastructure in the form of telegraph lines, vulnerable enough to reveal its practical consequences in such vivid, well-documented detail. He continued his sunspot observations for several more years after 1859, and in 1863 published what would become his most lasting scientific contribution, a detailed study demonstrating that the sun does not rotate as a single solid body, but spins faster at its equator, completing a rotation in roughly 25 days than near its poles, where a rotation takes closer to 35 days, a phenomenon now called differential rotation, understood today as a direct consequence of the sun being a fluid body of plasma rather than a rigid sphere. That 1863 publication, titled Observations of the Spots on the Sun, drew on more than a decade of the same careful daily position measurements that had put him at his telescope on the morning of September 1st, 1859, compiled into what remains, even now, one of the most complete individual records of sunspot activity ever assembled by a single observer working without any institutional support. Differential rotation turned out to matter far beyond simple curiosity about the sun's spin. It is now understood to be one of the essential ingredients driving the sun's entire magnetic cycle, since the equator's faster rotation gradually stretches and winds the sun's magnetic field lines with each passing rotation, generating exactly the kind of twisted, energy-storing structures that, when they finally break, produce events like the flare Carrington had witnessed years earlier, without yet understanding why such things happened at all. That discovery, built on the same painstaking daily measurements that had put him at his telescope on the morning of September 1st, 1859, remains foundational to modern solar physics, cited in research explaining the very magnetic processes that drive flares and coronal mass ejections in the first place. His personal life after 1859 grew considerably more difficult. Family financial troubles following his father's death drew him away from full-time astronomy in the years that followed, and his personal observatory at Red Hill was eventually sold, its daily observations ended. The brewery his father had built, which had funded Carrington's entire scientific career, required his direct attention after 1858, pulling him gradually away from the disciplined daily routine at the telescope that had made his earlier work possible in the first place. It is a quietly familiar kind of ending for a certain type of 19th-century amateur scientist, a career built on inherited wealth and personal discipline, ultimately curtailed not by any failure of the science itself, but by the ordinary financial pressures of the family that had made the science possible to begin with. He died in 1875, at the age of 49, having lived only long enough to see the earliest stirrings of the scientific field his own careful, patient observation had helped to found, a field that would not fully mature until well into the following century, when spacecraft finally allowed scientists to watch the sun's violent outer atmosphere directly, rather than waiting, as Carrington once had, for a lucky, unrepeatable glimpse through a telescope on an ordinary morning. The world Carrington left behind in 1875 was still one lit largely by gas lamp and candle, its long-distance communication still built on the telegraph wires that had so briefly and strangely become an unwitting instrument in his greatest discovery. It was not yet a world that depended on continuous, uninterrupted electricity for nearly everything, on satellites in constant orbit overhead, or on a navigation system reliant on radio signals sent down from space. All of it, unlike a 19th-century telegraph line, potentially vulnerable in ways far more consequential than a scorched length of paper tape or a spinning compass needle. That difference between the world the Carrington Event struck in 1859 and the world it would strike if it happened today is where this story turns next. What follows is not a prediction and not a forecast of any particular date or year. It is a hypothetical scenario built from published estimates by space agencies, power engineers, and insurers who study this exact question, useful not because anyone knows when the next Carrington-scale storm will arrive, but because it clarifies exactly what is different about the world it would strike. Estimating how often such a storm might occur at all is itself an active area of research. A 2012 study published in the journal Space Weather, analyzing more than 50 years of solar activity records, estimated the probability of a Carrington-scale storm striking Earth at somewhere around 1 in 8, or roughly 12%, in any given decade. That figure carries real uncertainty, drawn from a relatively short observational record applied to an inherently rare category of event, but it is treated by space weather researchers and infrastructure planners as a serious enough possibility to justify continued study rather than a remote curiosity safely confined to history. The first difference is the electrical grid itself, a piece of infrastructure that did not exist in any meaningful form in 1859, and that now underlies nearly everything modern life depends on. A geomagnetically induced current behaves the same way today as it did in a 19th-century telegraph wire, arising from the same principle of electromagnetic induction described by Faraday decades before Carrington's flare. The difference lies in what that current now flows into. Instead of a telegraph key designed to carry a gentle battery current, a modern GIC flows into enormous high-voltage transformers, machines that step electricity up and down in voltage as it moves across the grid, each one built to extremely precise specifications for handling smoothly alternating current, not the slow, steady, direct current-like surge a geomagnetic storm can inject. When that surge enters a transformer, it can push the machine's internal magnetic core into a condition called half-cycle saturation, in which the core briefly stops behaving the way its design assumes, drawing far more current than intended and generating intense, localized heat within windings never designed to handle it. In smaller storms, this simply causes a transformer to run hot for a period, a manageable, monitored condition. In a sufficiently powerful and prolonged storm, that heat can permanently damage or destroy the transformer, and large power transformers of the kind used at major grid substations are not simple off-the-shelf components. Each one is typically custom-built for its specific substation, weighing hundreds of tons, and manufactured to order by a small number of specialized facilities worldwide, a process that engineering assessments have estimated can take many months, and in some cases well over a year, from order to installation. Unlike smaller grid components, these transformers are rarely kept in significant reserve, since each substation's transformer is typically engineered to that location's specific voltage and load requirements, making a large, standardized stockpile of spares impractical under ordinary utility budgeting. Some grid operators and government agencies have, in the years since the 2008 study, begun stockpiling a limited number of standardized emergency transformers designed to be adaptable across multiple substations, a direct policy response to exactly this vulnerability, though assessments generally agree that current reserves remain far smaller than what a truly widespread Carrington-scale event would require. A 2008 study commissioned by the United States government, conducted by the National Academy of Sciences, examined exactly this scenario, a Carrington-scale geomagnetic storm striking the modern North American power grid. The study's authors estimated that a storm of that magnitude could damage or destroy a significant number of the large transformers underlying the American grid, potentially leaving parts of the country without reliable power for a period the report described in terms of months to years, rather than the hours or days typical of an ordinary storm-related outage, given the long lead times required to manufacture replacement transformers at scale. The same study estimated the potential economic impact of such a scenario in the range of $1 to $2 trillion in the first year alone, a figure driven less by the storm itself than by the cascading effects of extended, widespread power loss on water treatment, refrigeration, communications, transportation, and nearly every other system a modern economy depends on continuous electricity to run. Water treatment plants, for instance, generally rely on continuous electrical power to run pumps and filtration systems, meaning an extended regional blackout could compromise clean water access well beyond the storm itself. A secondary effect the 2008 study specifically highlighted as a significant risk multiplier in any extended outage scenario. Insurers have conducted their own independent assessments of the same basic scenario. A widely cited 2013 analysis published by Lloyd's of London, examining the insurance industry's exposure to a Carrington-scale storm striking the United States, arrived at broadly similar conclusions regarding both the number of transformers potentially at risk and the extended timeline required for recovery, treating the scenario as a genuine, insurable catastrophic risk rather than a purely theoretical exercise. That same analysis attempted to estimate how many people within the United States could lose power under a range of possible storm severities, producing figures ranging from a relatively contained regional impact in a milder scenario up to tens of millions of people in the most severe scenario modeled, underscoring how heavily the ultimate outcome depends on factors, including the storm's precise magnetic orientation and timing, that remain fundamentally unpredictable in advance. It is worth noting that this remains an estimate, built on modeling rather than direct experience, since no storm of Carrington's scale has struck the modern grid to confirm it. The closest real-world comparison available comes from a considerably weaker storm. In March of 1989, a geomagnetic storm reaching a DEST value of roughly negative 580 nanotesla, well below the negative 1600 to 1800 nanotesla estimated for the Carrington event, caused a rapid cascading failure across the Hydro-Quebec power grid in Canada, leaving roughly 6 million people without electricity within a span of about 90 seconds, an outage that lasted around 9 hours before power could be restored. That single, comparatively moderate storm offered a real, measured glimpse of how quickly a modern grid can fail once GIC-driven currents begin pushing transformers and protective relays beyond their designed limits, a preview engineers now study closely when modeling what a storm several times stronger might do. The Quebec blackout began, according to utility records, within roughly 90 seconds of the storm's peak intensity reaching the region, a speed of onset that left grid operators almost no time to respond manually, even with modern monitoring equipment already in place, a detail that continues to shape how engineers think about the earliest, most critical minutes of any future severe storm. Space itself presents a second modern vulnerability that had no equivalent whatsoever in 1859, since nothing built by humans yet orbited the planet. A major geomagnetic storm heats and expands Earth's upper atmosphere, increasing atmospheric drag on objects in low orbit, including the thousands of active satellites that now provide communication, weather forecasting, and navigation services worldwide. During the geomagnetic storms of late October and early November 2003, sometimes called the Halloween storms, increased atmospheric drag was significant enough that engineers at NASA and other space agencies temporarily lost precise tracking of a substantial number of objects in low Earth orbit, satellites and debris alike, as their orbits shifted more than ground-based tracking models had accounted for. A storm of Carrington scale would be expected to produce a considerably larger version of the same effect, potentially degrading the accuracy of satellite tracking across the board and increasing collision risk between satellites and debris for a period afterward, according to assessments published by space agencies studying the scenario. Global positioning satellites, relied upon today not only for personal navigation, but for precise timing signals, underlying banking transactions, power grid synchronization, and telecommunications networks, are themselves vulnerable to the ionospheric disturbances a major storm produces. Financial systems in particular depend on GPS timing signals to an extent not widely appreciated outside the industry, since many high-speed trading and interbank transaction systems use those signals to timestamp transactions with the precision needed to establish their exact sequence, a function separate from the navigational use of GPS most people are familiar with. A significant sustained degradation of GPS timing accuracy during a severe storm could therefore introduce complications into financial infrastructure well beyond anything related to maps or directions, a secondary consequence that space weather researchers have increasingly studied as its own distinct category of risk. The same charged particles that would paint the sky with aurora also disturb the ionosphere, the electrically charged layer of the upper atmosphere that GPS signals must pass through on their way from satellite to receiver, introducing timing errors that can degrade positioning accuracy from its usual precision of a few meters to errors of tens of meters or more for a period during and after a severe storm. Astronauts aboard the International Space Station face a more direct hazard since they orbit above much of the atmospheric shielding that protects people on the ground from energetic particles. During significant solar particle events, space agencies already direct astronauts to shelter in more heavily shielded sections of the station, a precaution taken during real, smaller storms in the current era, one that would become considerably more serious during an event of Carrington-level intensity. Long-distance undersea communication cables, which now carry the overwhelming majority of international internet traffic beneath the world's oceans, represent a further modern vulnerability entirely absent in 1859, since no such cables existed at any meaningful scale. These cables include repeater stations spaced at intervals along their length, electronic equipment that amplifies the signal as it travels thousands of kilometers underwater, powered by a continuous electrical current sent through the cable itself from stations onshore. Researchers studying space weather risk have noted that geomagnetically induced currents could, under sufficiently severe storm conditions, disrupt or damage these repeater systems in ways broadly similar to their effect on power grid transformers, potentially severing or degrading long stretches of the undersea cable network that much of the modern internet depends on for connecting continents. Because undersea cables of this kind run for enormous distances, often thousands of kilometers between shore stations, they present exactly the sort of long conductor loop most susceptible to a storm's induced currents. The same basic vulnerability that made the Boston to Portland telegraph line so responsive to the 1859 storm now applied to infrastructure carrying a global economy's data rather than a single city's telegraph traffic. Long-distance oil and gas pipelines face a related, though distinct, risk. Pipeline operators already monitor for a phenomenon called pipe-to-soil potential, a natural electrical difference between a buried pipeline and the surrounding earth that utilities manage carefully to prevent corrosion. A strong geomagnetic storm can significantly disturb that natural balance, and engineering studies of pipelines, including the Trans-Alaska Pipeline System, have found that geomagnetically induced currents during storms can accelerate corrosion processes and, in some documented cases, interfere with the pipeline's automated monitoring and control systems. In July of 2012, a coronal mass ejection with a strength comparable to the 1859 storm erupted from the sun and narrowly missed Earth, sweeping instead past NASA's Stereo A spacecraft, positioned at the time in roughly the same orbital location Earth had occupied just over a week earlier. Stereo A's instruments, built specifically to measure exactly this kind of event, survived the encounter and recorded detailed data on the cloud's speed, magnetic orientation, and particle density, giving scientists their clearest direct measurement yet of what a Carrington-class storm actually looks like from the inside. Researchers who studied that data concluded that had the eruption occurred roughly 9 days earlier, when Earth itself occupied that same point in its orbit, the resulting storm would very likely have matched or exceeded the intensity of the Carrington Event, a near miss separated from a modern-day repeat of 1859 by little more than the sun's own timing. Physicist Daniel Baker, who led one of the research teams analyzing the 2012 event, noted in subsequent published commentary that the storm appeared, by every measurable parameter, to have been at least as powerful as the one Carrington had witnessed a century and a half earlier, differing only in the simple fact that it happened to miss the planet entirely. In the years since that 2012 near miss, engineers and grid operators have begun taking more concrete preparatory steps than existed at the time of the 2008 National Academy study, including the development and, in some regions, the installation of devices called neutral blocking devices, designed to interrupt the path geomagnetically induced currents taken to a transformer's grounding system before they can build to damaging levels. Regulatory bodies overseeing the North American power grid have also, in the years since, established formal standards requiring utilities to assess their own vulnerability to geomagnetic disturbances and develop operating procedures for reducing grid stress during a forecasted storm, incremental but genuine steps toward hardening a system that, as recently as 2012, had few such protections in place at all. None of these measures eliminate the risk entirely, and assessments generally agree that a storm matching the full intensity of the Carrington event would still cause serious widespread disruption, even to a modern, better prepared grid, but they represent a meaningful shift from where infrastructure planning stood only a little over a decade ago. Air travel presents a final, quieter modern vulnerability. Commercial aircraft flying polar routes, the shortest paths between many cities in North America, Europe, and Asia, already fly through regions where Earth's magnetic field funnels solar particles most directly into the atmosphere, exposing crew and passengers to elevated radiation and occasionally disrupting high-frequency radio communication used for polar navigation. During significant solar particle events today, airlines already reroute some polar flights to lower latitudes as a standard precaution, a real current practice rather than a hypothetical one, adopted specifically because of the radiation and communication risks such storms pose at high altitude and high latitude. Airlines generally rely on space weather alerts issued by aviation-focused forecasting centers to make these rerouting decisions in near real time. A coordination system built specifically because polar routes, while shorter and more fuel-efficient under normal conditions, become measurably riskier during periods of elevated solar particle activity, even for the relatively modest storms that occur several times in an average year. A storm of Carrington scale would be expected to make polar flight impractical for a period of days, according to aviation safety assessments, requiring widespread rerouting across the busiest long-haul air corridors connecting the Northern Hemisphere's major cities. Rerouting a polar flight to a lower latitude path typically adds meaningful flight time and fuel consumption, and during a sustained storm lasting several days, aviation researchers have noted that the cumulative effect across an entire industry's global schedule could produce significant delays and cost, layered on top of whatever ground-based disruptions a severe storm was simultaneously causing to airport power and communication systems. High-frequency radio, still used for long-distance communication with aircraft over oceans and polar regions beyond the range of ordinary radio and satellite links, is itself degraded by the same ionospheric disturbance that affects GPS signals, since HF radio depends on that same charged layer of the upper atmosphere to reflect signals back toward Earth across long distances. During a sufficiently severe storm, that reflection can be disrupted entirely for a period, a phenomenon called a radio blackout, cutting off one of the few remaining communication methods available to aircraft and ships operating far from land-based infrastructure at precisely the moment other systems might also be failing. Taken together, these vulnerabilities describe a world considerably more exposed in some respects than the Telegraph-era world the actual Carrington event struck, even though that same modern world also possesses tools 1859 never had. It is a strange kind of trade, one modern civilization has made largely without realizing it. Enormous gains in speed, connectivity, and capability, purchased at the cost of a new and largely invisible dependence on a handful of physical systems, transformers, satellites, undersea cables, but a sufficiently powerful storm from 93 million miles away could still reach and disrupt, much as it once reached a length of copper wire strung between Boston and Portland. Spacecraft positioned between the Sun and Earth, most notably one called Discoveer, stationed roughly 1 million miles sunward of Earth at a gravitationally stable point in space, now provide real-time measurements of incoming solar wind conditions, typically offering warning of an approaching storm's most severe effects somewhere between 15 minutes and an hour before arrival. D'Escovir sits at what is known as the first Lagrange point, a location where the gravitational pull of the Sun and Earth balance in a way that allows a spacecraft to remain in a stable position relative to both, continuously facing the Sun and directly in the path of any solar wind or coronal mass ejection heading toward Earth. From that vantage point, D'Escovir and a small number of companion spacecraft measure the speed, density, and magnetic orientation of incoming solar wind moments before it reaches Earth, data that is relayed to NOAA's Space Weather Prediction Center in Colorado, where forecasters issue alerts to power grid operators, satellite companies, and airlines around the clock every day of the year. It is a narrow window, far too short to manufacture and install a damaged transformer, but long enough, space weather forecasters note, to take certain protective measures, adjusting power grid configurations, powering down especially vulnerable satellite systems, and alerting airlines to reroute flights already in progress. 15 minutes to an hour is not very much time at all. It is, however, considerably more warning than Richard Carrington had, watching two beads of white light fade from his telescope with no way of knowing that a storm was already 18 hours from striking his world without any notice whatsoever. The sky tonight carries no such storm. Modern instruments are watching it closely all the same, continuously, from orbit and from the ground, in a quiet, uninterrupted vigil that traces its own lineage back to a magnetized needle jumping on a strip of paper at Kew Observatory, more than a century and a half ago. Spacecraft including NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter now fly closer to the Sun than any human-made object ever has, gathering data on the very magnetic processes, the twisting, the reconnection, the eruption that once played out invisibly above Richard Carrington's head as he sketched sunspots through a modest refracting telescope in the English countryside. Between those spacecraft, the D'Escovir satellite watching from its stable point in space, and the ground-based magnetometer network descended from Humboldt's original magnetic crusade, the Sun's activity is now observed more continuously and more completely than at any point in human history. The vigilance is real. What it is watching for tonight is quiet. Somewhere on the Sun tonight, unnoticed, the same basic processes that produced Carrington's flare are still turning. The Sun is not a fixed, unchanging light. It moves through its own long rhythm, a cycle of roughly 11 years, rising from a hushed minimum of few sunspots and settled magnetic fields, toward a more active maximum and back again. That cycle is currently in its 25th numbered count since astronomers began formally tracking it in the 18th century, a slow, unbroken counting that stretches back through every solar maximum and minimum since long before Carrington ever built his observatory at Red Hill. The current cycle began in late 2019, rising gradually through the early 2020s toward a peak of activity that solar physicists placed around 2024 and 2025, and it is now slowly beginning its long descent back toward the next still minimum. Solar minimum, when it arrives again in the early 2030s, will bring with it weeks and sometimes months where the Sun's face shows almost no sunspots at all, a bare, uneventful surface offering little of the tangled magnetic complexity needed to produce anything like a Carrington scale flare. Even now, well past this cycle's peak, most days pass with the Sun's activity registering as entirely unremarkable on every instrument watching it, and even baseline occasionally interrupted by smaller, far less consequential flares that come and go without incident. On a day such as this one, a handful of minor flares might rise and fade on the sun's surface without a single satellite operator or grid engineer needing to take any notice at all. Small, forgettable events dwarfed by comparison to the one Carrington happened to witness. Most days, most cycles, most decades, the sun simply turns, releasing its energy in the same unbroken stream of light and warmth that has reached Earth every day for more than 4.5 billion years. The flares happen, the coronal mass ejections happen. Almost all of them miss Earth entirely, sent outward in a direction that has nothing to do with the small blue planet orbiting 93 million miles away. Even the ones that do reach Earth are overwhelmingly gentle by comparison to 1859, producing nothing more than a faint aurora glimpsed by observers already watching for it in Alaska or northern Norway. The sun that produced the Carrington Event is the very same sun visible right now wherever daylight currently falls somewhere on Earth. It has not changed its nature. It simply, on one particular morning in 1859, happened to release one particular, extraordinary burst of energy in the direction of a planet whose people had just finished stringing the first thin threads of copper wire between their cities. In, out. Earth's magnetic field has been standing between that sun and the surface of this planet for billions of years, generated continuously by the slow, patient churning of molten iron and nickel deep within the core, exactly as it was in September of 1859, exactly as it is tonight. Scientists who study the planet's ancient magnetic history, a field called paleomagnetism, have found that this protective field has occasionally weakened and reversed its polarity entirely over the vast span of Earth's history, north becoming south and south becoming north, a process that unfolds gradually over many thousands of years rather than suddenly. The most recent such reversal took place roughly 780,000 years ago, long before any human being existed to notice it, and the field has remained in its current orientation, strong and stable, throughout the entire span of human history, including every single year since Carrington first sat down at his telescope. Compared to many other stars scattered across the galaxy, the sun itself is, in its own way, remarkably even-tempered. Astronomers classify the sun as a G-type main-sequence star, a mid-sized, moderately bright category of star that burns its hydrogen fuel evenly and predictably, without the violent, unpredictable flaring common to smaller, cooler stars called red dwarfs. Many red dwarf stars, though far fainter than the sun, produce flares proportionally far more powerful and far more frequent, sometimes releasing bursts of radiation strong enough to strip away the atmosphere of any nearby planet entirely, a fate the steadier, more even-tempered sun has never come close to inflicting on Earth across 4.5 billion years of orbit. In the plain arithmetic of stellar behavior, the star that produced the Carrington Event still ranks, on the whole, among the gentler ones. The sun's 4.5 billion year shine comes from a process happening deep within its core, where immense pressure and temperature fuse hydrogen atoms into helium, releasing energy that slowly makes its way outward through hundreds of thousands of kilometers of solar material before finally reaching the surface as light. That journey from core to surface is so slow, so thoroughly diffused and reabsorbed along the way, that a single photon of light can take many thousands of years to travel from the point of its creation to the moment it finally escapes into space, only to cross the remaining 93 million miles to Earth in a brief 8 minutes once it is finally free. In a very real sense, the sunlight falling on the Earth tonight, wherever daylight currently touches the planet, began its journey inside the sun long before Carrington was born, long before the telegraph existed, long before most of what this story has described. It is a slow, patient kind of light, built from a process that has repeated itself without interruption for 4.5 billion years and shows no sign, according to current stellar models, of doing anything but continuing for billions more. That shield has never once failed completely, even during the Carrington Event, even during the strongest geomagnetic storm ever recorded. The magnetosphere held, compressed and battered but intact, allowing the atmosphere beneath it to remain exactly as breathable, exactly as stable as it always had been. The telegraph wires suffered, the compasses spun, the sky itself turned strange and red over Havana and Bombay. The planet itself, underneath all of that, simply continued turning the way it always has, the way it still does tonight. Aurora is still out there right now, unseen by most, somewhere near the poles, a small, gentle version of the same physical process that once lit up half the world in 1859. Charged particles, funneled down along invisible lines of magnetic force, still meet the thin upper atmosphere in a soft collision, releasing their extra energy as light, exactly as they did that night, only smaller, milder, closer to the poles where such displays belong. Somewhere in northern Norway tonight, or in Alaska, or in the far south near Antarctica, that faint green light may be moving slowly across the sky right now, watched by a handful of people standing outside in the cold, entirely unaware of and entirely unthreatened by any of what once happened in 1859. In towns like Tromsø, in the far north of Norway, or Fairbanks, in central Alaska, watching for that faint green light has become a familiar part of local life, a nightly possibility during the darker months, checked the way people elsewhere might check the chance of rain. Local guides and residents in these places watch space weather forecasts issued by agencies like NOAA's Space Weather Prediction Center, the same kind of forecast built to warn power grid operators of danger, used here for a gentler purpose entirely, knowing which night might be worth stepping outside for. On an illustrative winter evening with a favorable forecast, a tour operator in a town like Tromsø might load a small van with blankets and thermoses and drive a group of visitors out past the edge of town, away from streetlight glow, to wait together in the dark for a display that owes its entire existence to the same charged particles once responsible for a red sky over Havana. It is the same physics, the same charged particles, the same magnetic funnel drawing them down toward the pole, put to a use as gentle and unhurried as anything in this story. Modern forecasters describe the likelihood of visible aurora on a given night using a simple scale called the KP index, running from 0, indicating essentially no geomagnetic activity, up to 9, indicating a storm severe enough to push aurora toward the middle latitudes. On most nights, the KP index sits somewhere between 0 and 2, describing exactly the kind of settled, unremarkable conditions Earth's magnetic field experiences the overwhelming majority of the time, aurora present only faintly and only very near the poles. That number, low and unremarkable, is itself a small ongoing act of reassurance, updated continuously, freely available to anyone who wishes to check it, a direct, measured answer to the question Carrington himself had no way of asking in 1859. What, exactly, is the sun doing to Earth's magnetic field right now? Tonight's reading, wherever it happens to fall, almost certainly belongs to that same familiar range, the sun continuing its long, patient turning, unremarkably, the way it does on nearly every night in nearly every year. It is the same aurora. It is simply, tonight, behaving the way it does on an ordinary night, rather than the way it did on one extraordinary one. In, out. A modern citizen science project called auroras, developed with support from NASA and the National Science Foundation, now invites ordinary people anywhere in the world to report aurora sightings in real time, an informal, distributed network of observers, not entirely unlike the scattered mix of astronomers, telegraph operators, and ship's captains whose separate accounts once helped piece together the full story of 1859. Where Carrington worked alone with a pencil and a projection screen, today's observers use a phone, a photograph, a simple report submitted from a backyard or a mountainside, each one a small data point feeding into a much larger, continuously updated picture of where the aurora is glowing on any given night. It is, in its own understated way, a direct descendant of the same impulse that drove Humboldt to build his global network of magnetic observatories nearly 2 centuries ago. The conviction that a phenomenon this vast can only be understood by many careful eyes watching together from many different places at once. There is something worth holding onto in that plainness, in the fact that the same sun capable of producing the most powerful storm ever recorded spends nearly all of its time simply shining, evenly, gently, exactly as it has for billions of years, exactly as it will again tonight and tomorrow night, and every night after that. Richard Carrington spent his career watching that familiar shining day after day for years, and it was only once in 5 minutes on a single September morning that anything extraordinary appeared at all. Even then, the extraordinary event did not break the world. It strained it, startled it, revealed its hidden vulnerabilities in a handful of telegraph wires and compass needles, and then, within a few days, it passed. The sky cleared. The aurora faded back to the poles where it belonged. The telegraph operators repaired what needed repairing and went back to sending their everyday messages down their familiar wires. Carrington went back to his sketches. The sun went back to turning, unremarked, as it always had, as it still does now. Picture, for a moment, that small observatory at Red Hill once more, not on the extraordinary morning of September 1st, but on any unremarkable morning before or after it. A telescope aimed carefully at the sun through a protective filter, a screen catching the projected image, a single observer, unhurried, tracing the outline of whatever plane or complicated sunspot group happened to be crossing the disk that day. Most mornings, nothing remarkable happened at all. The sun simply turned, the spots simply drifted slowly across its face, and Carrington simply recorded what he saw, one more entry in a long, patient table of numbers. That patience, sustained across years of unremarkable mornings, is what made the one extraordinary morning possible to witness and record at all. It is a useful thing to remember about most of science, and perhaps about most of life. The remarkable moments rest on top of a great deal of patient, careful, unremarkable attention paid consistently, long before anyone knows whether it will ever be rewarded. Most nights end exactly the way most nights begin, uneventfully. Without incident, the instruments recording nothing more dramatic than the familiar gentle hum of a planet and a star going about their long shared routine together. The telegraph operators who once found their line carrying the sky's own current briefly on one strange night in 1859 went back the next day to sending routine messages down familiar wires. The extraordinary interruption folded back, without fuss, into the pattern of daily work. The compasses that once spun freely settled back to true north, the night skies over Havana and Bombay, and the Rocky Mountains returned to their familiar darkness, unremarkable once more. 167 years is a long time by the measure of a single human life. It is nothing at all by the measure of the sun. The star at the center of this solar system has been shining for roughly 4.5 billion years, and current models suggest it has enough hydrogen fuel remaining to continue shining, largely unchanged, for another 5 billion years beyond tonight. If the sun's entire lifespan, past and future combined, were compressed into a single unremarkable day, the moment Carrington watched his flare would fall somewhere in the final few thousandths of a second before midnight, a sliver of time too small to meaningfully register against a story that long. Every flare, every coronal mass ejection, every storm as powerful as the one that reached Earth in September of 1859, is a single brief flicker within a much longer, far steadier story, one that began long before telegraph wires, long before human beings, long before Earth itself had finished forming. Nearly 167 years after that particular flicker, the same sun is still there, 93 million miles away, exactly where it has always been. Tonight, conditions are settled. The magnetometers, watching continuously from stations scattered around the globe, are recording even unbroken lines. At NOAA's Space Weather Prediction Center in Boulder, Colorado, a small team of forecasters keeps watch around the clock, every night of the year, in a role that traces its lineage directly back to Balfour Stewart, bent over the Q magnetometer's photographic strip. Screens there display real-time readings from satellites, ground stations, and the DSCOVR spacecraft watching from its stable point in space, a continuous, unhurried stream of data confirming night after night that conditions remain within their familiar range. Most shifts pass exactly like this one, even readings, unbroken lines, nothing requiring an alert to be issued to any power grid operator or airline anywhere in the world. It is unglamorous, largely invisible work, the modern continuation of a habit of careful watching that stretches back through Balfour Stewart, through Humboldt's magnetic crusade, through Gauss and Weber's coordinated observatories, all the way to a single astronomer in Surrey who simply wanted to know where the sunspots were each morning. The satellites are stable in their orbits. The power grid is humming along exactly as it should. Far to the north, a thin curtain of green light might be moving slowly across a dark sky, gentle and unhurried, a small, faint echo of the very same force that once reached all the way to Cuba. Deep beneath the ice sheets of Greenland and Antarctica, the layer marking 1859 rests exactly where it has rested for more than a century and a half, undisturbed, a faint chemical signature of the night the sky turned red over the Caribbean, waiting patiently should anyone ever wish to read it again. No one needs to read it again tonight. It simply rests there undisturbed, one small, settled piece of evidence in a planet that keeps a great many such records, layered in ice, etched in old ship logs, pressed into the yellowing pages of 19th-century telegraph reports, none of it urgent, all of it simply waiting. At Red Hill, in Surrey, the observatory Carrington once built no longer stands, sold off and gradually lost to time, not long after his own life grew difficult. But the sky above that unremarkable patch of English countryside is exactly the same sky he once watched, the same sun rising and setting across it every day, unchanged in any way that matters. If a visitor were to stand today on the general site where that observatory once looked skyward, they would find, most likely, an unremarkable stretch of English suburb, houses and gardens, where a telescope dome once stood, with nothing to mark the exact spot where two beads of white light were first seen and recorded by human eyes, a small illustrative reminder of how little physical trace even a history-making observation tends to leave behind. Tonight, an amateur astronomer, not so different from Carrington himself, may be tracking sunspots of their own without fanfare, continuing, without perhaps even realizing it, a tradition of patient, careful watching that stretches back through Aurorasaurus, through Noah's forecasters in Boulder, through Bulfer Stewart at Kew, all the way to a brewer's son in Surrey with a telescope and a projection screen. They will not, most likely, see anything as dramatic as two beads of white light tonight. Almost no one ever does. That is, in the end, the familiar and reassuring shape of most scientific watching, long stretches of unhurried observation, faithfully repeated, rewarded only rarely, and only ever by chance, with a morning like September 1st, 1859. The story that began with two beads of white light on an ordinary September morning has, across 167 years, become something larger than any single observation, a slow, careful, ongoing act of watching carried forward by generation after generation of people who simply wanted to understand what the sun was doing and what it might mean for the small, unassuming planet turning beneath it. Tonight, that watching continues unhurried as it always has. Far above, the sun keeps turning. Far below, the core keeps churning, generating the invisible shield that has held for billions of years. Between them, on the surface of a small planet lit by starlight 8 minutes old, the wires sit undisturbed, the compasses hold true, and the sky for one more unremarkable night is exactly as it should be. This is Quiet Science at Bedtime. If tonight's story kept you company, a subscribe helps this channel keep telling stories like it, and it costs nothing at all. Everything you heard tonight is real. The sun is out there right now. Sources and further reading for anyone who would like to explore tonight's story further. What was the Carrington Event? From NOAA's National Environmental Satellite Data and Information Service, available at nsdis.noaa.gov. Near Miss, the solar superstorm of July 2012, from NASA Science, available at science.nasa.gov. The Carrington Event entry on Wikipedia, available at n.wikipedia.org, which includes citations to the original scientific literature for anyone who wants to go deeper still. In, out. The wires are quiet tonight. The sky is quiet tonight. Sleep well. Good night.